Here we are in section 1.2, and we're talking about row reduction and echelon form. Perhaps you've done some of this in other classes when you've solved matrices, and you probably just use your text and friend. Definition: a rectangular matrix is in echelon form or row echelon form if it has the following three properties. So first of all non-zero rows are above any rows of all zeros. If you have these zero rows like that, they're going to be at the bottom. That's what the first thing is saying. Second, each leading entry of a row is in a column to the right of the leading entry of the row above it. So we would call these the ones here. We would call these the leading entries. And you can see leading entries in the examples below as well. So these are all leading entries. And you'll notice that those leading entries are all the ones farthest to the left are at the top, and the ones farthest to the right are at the bottom. So that's what this bit here is saying. Each leading entry of a row is in a column to the right of the leading entry of the row above it, basically saying you're going to move from left to right. Third, all entries in a column below a leading entry are zeros. So here you have zeros, 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 zeros. There's everything below one of those boxes is so all of these qualities are for echelon form. And so we can add a couple of additional qualities if we're going to be in reduced row echelon form. Here we've got the reduced row echelon form. And so, what color haven't I used? Pink. So the leading entry in each the leading entry in each non-zero row is 1. And so you'll notice that in the reduced row echelon, we have the pink. Above, we have the pink 1. Above, we had the box. It could have been any number that wasn't 0. Each leading one is the only non-zero entry in its column. So you'll notice that above, see how you have the little stars there saying you could have some random number above a leading one, but in the reduced row echelon form, you have to have a 0 above. So notice you've got the zeros above the leading ones as well. But you could have the stars represent kind of like random stuff. It could be any number, including 0. That's any number, including 0. Questions about echelon form, reduced echelon form, reduced row echelon form? Let's see, from Hui, is there a chance that two rows have a same leading point location? Can you clarify that question, Hui?
I mean, like in this case, like each row have a different different location of leading point. Like, is there like a chance of having it, or we just making mistake for it to happen?
You're saying in this case you have those leading spots happening in different places, but could they ever be in the same
Like
spot?
same column, yes, same column.
Yeah, no, they will. If you follow the algorithm, they will never be in the same column. Benjamin asked, is there a benefit from each form? If you're doing things on for our purposes, we will pretty much do things entirely in terms of reduced echelon form or reduced row echelon form. If you were doing things by hand, you might use one of the other forms because you could save yourself writing some stuff. If you're doing it by a computer and you had, say, 5 million row matrix by 10 million column matrix, you might want to use one of these other methods because it would be save you some computational power. But in general, we're just going to use the reduced echelon. In the echelon form, what these boxes represent is they represent any number except 0. Any number but not 0. So that's what the black boxes represent. Then when we go to the reduced echelon form, what we're saying is it can't be any number, it has to be a 1. Did that answer your question, Andrew? And it looks like answered your question, Calvin. So non-zero matrices can be row reduced into many different matrices in echelon form. So I think this is the answer to Adis's question about whether it would be unique. But the row reduced echelon form or the reduced row echelon form is unique. There's only going to be one version of it. Here's the theorem. It says, from Elijah, what does the asterisk represent as far as elements go inside the matrix? The asterisk represented any value. It could be any number other than, any number, including 0, including 1. So let's see if we can run through one more example here. So each matrix is row equivalent to one and only one reduced echelon matrix. So we want to row reduce the matrix to echelon form and locate the pivot columns. Our pivot columns, we're going to note with, we'll box with some green as we go along. And so here's my first pivot. Okay. And what I would like to do is I would like to, because I'm trying to get into echelon form, notice this is not reduced echelon form. What I need to do is I need to get zeros in all of these yellow spaces. And this is going to be a little bit odd because I don't have a leading 1. Do you guys want to get a leading 1? That'll make our lives a little easier, I guess. So if I want to get a leading 1 in the second row, what I could do is I could take 3 of row 2 and I could add it to row 1 and I could make a new row 2. First row is the same. Second row is now going to be 0, 4, 0, 4, negative 12, 4, 7, and 7. In our third row, we can, again, we have a negative 1. We're going to try to use the value that's in, well, actually, I've got this 1 and negative 1, so we can just add those together. So that'll make our lives easy. So I could just do row 3 plus row 2 is going to give me a new row 2, or row 3. In our third row, we could add rows 3 and 4. Give ourselves a new fourth row. I think I said third, I meant fourth, I'm sorry. And what I want to point out is that yellow stuff is now all zeros. Okay, so we have our first pivot right here. Notice it's a non-zero number with zeros below it. So I worked through the end of the question that we started on yesterday, and I wanted to highlight some things, and then we're going to move on to another example, which I think is probably a more helpful example to you. So I just want to pull out a couple things in this. So the first thing I want to point to is I want to point to the kind of the goal. What we did was we started with the -3, 1, -1, 1 in column 1. And then after our first step, we ended up with the -3, 0, 0, 0. So we got the zeros underneath. The fact that we have a leading 1 and then, a leading non-zero and then zeros below tells us that this is a pivot column and that the pivot is -3. So then we go to the next step and we see this 4 that's here. And so our goal is to get zeros below. So we keep, in this case, we're keeping the 4 and we've got zeros below. We're focusing in on that second column. And that tells us again that our second column is a pivot column. And now the pivot is 4. Column is 2, it's the second column, and the pivot is 4. And then after we do all that row reduction, notice that you have all these zeros all the way over to the 5th column. And so this is going to be our last pivot column. And what we do to it is we again get the 0 in that green spot right here, leaving us with one more pivot column and the pivot being -5. So the columns are 1, 2, and 5, and the pivots themselves are, what are they, -3, 4, and -5. So far, so good on pivot column. Like, I haven't explained process, but so far, so good on identifying the pivot columns and the pivots themselves. The other thing I wanted to comment on is just the why I multiplied or how I multiplied by what to get a 0. And so there's lots of places we could look, but let's just look at this last example right here. If I'm trying to get a 0 at some level, what I'm doing is I'm using the pivot that's right here to eliminate the number that I'm trying to get rid of, to eliminate the number below it. And so this -5 is, I'm multiplying by the next row down, and then the 41 is being used on the pivot row. So effectively, I'm saying 5 times 41 minus 41 times 5. Like, that's sort of the strategy that I'm using. You'll notice that if these two critters have the same sign, ooh, that did not work. Notice these guys if they have the same sign, then you're going to end up with a plus and a minus. If they already had if they had opposite signs, like right here, you have a -3 and a 1. They're already opposite signs. And so we're going to end up with a plus and a plus.
I have a question.
Go ahead.
Can we scale down like the 4th row?
Sure, to be like 1, 1.
Yeah.
Of course. And we're going to do that in the next example.
Oh, okay.
Yeah, this was a little bit of an odd example because all I was trying to do was identify the columns and the pivots. I wasn't actually trying to do a full row reduction.
Oh, okay. Okay.
Let's look at example 3. What's our first thing we're trying to get here? So from Ben turning column 1 into a pivot column, that sounds good. And specifically a pivot column with pivot equal to 1. So we want that first pivot to equal 1. So there's lots of ways that we could accomplish that, but one way to accomplish it would just be to take advantage of the 1 that's already here. Probably can see that -1 there in the second column, or sorry, in the second row. And so you're like, well, I wish that was in the first row. Good news, we can make it happen. We're going to have -R2 is going to become our new R1. We'll have 1 minus 2 plus 1 minus 2 5 minus -5 positive 13. So that took care of our first row. Now we need to get zeros in the rest of column 1. And so to get zeros in the rest of column 1, we could, for example, take our first row and add 2 of the second row. I could take row 1 plus 2 row 2s and make that a new row 2. And I'm looking at the old row 1 here. 2 plus negative 2 is 0. Negative 4 plus 4 is 0. 3 minus 2 is 1. Negative 4 plus 4 is 0. Negative 11 plus 10 is 1. 28 minus 26 is 2. So I feel like there's one sign issue. Is this a minus 1? So then we can keep row 3 the same. Row 3 was already had a 0 in the correct spot. So we have 0, 0,
3, 1, 6, minus 10.
and then last but not least, we want to get to replace the 3, and so we can use maybe use row 2 to eliminate row 4, the 0 in row 4. We'd have row 4 plus row 2 to row 4. Scary R.
4, 7, 2,
61 minus 39. I think I got a negative here. Let's check. All right. So from Ben, if we switched row 2 with row 1, should we say row 1 instead of 2? Here, all of these operations that we're doing are on the basis of the original matrix. And so we did all of these operations on the basis of the original matrix, basically 3 steps in one, and now we've got a new matrix that is row equivalent. And again, why did we do that? We did that because we wanted to have the pivot be a 1, and we wanted everything below the pivot to be a 0. And we've accomplished that. So then moving forward, we got to figure out what's next. Do we need to do anything in column 2? Anything needed in column 2? Nope, column 2 is happy. Okay, there's no pivot there. Then we move over to column 3. Do we need to do anything in column 3? Yes. There's one good thing that's already true in column 3. What's the good thing? Yeah, we already have that our pivot is 1, so we're happy about that. Now we just need to knock off the negative 3 and the 7 that are below. So if we focused in on row 3, we're going to have row 3 plus 3 row 2 becomes our new row 3. Okay, so we're here. And we're trying to replace rows 3 and 4. So row 3 plus 3 row 2 is going to be the new row 3. And so we're going to end up with 0 again. We're going to end up with 0 plus 3 zeros is 0. Negative 3 plus 3 times 1 is 0. 1 plus 3 times 0 is 1. 6 minus 3 is 3. And minus 10 plus 6 is minus 4. If we want to get rid of the 7, we'll do row 4 minus 7, opposite sign, row 2 goes to row 4. And so all the 0, if you do this right, all the zeros stay where they're supposed to. Now you have negative 2 minus 7 or minus 9, minus 13, minus 42. I feel like I did something wrong here. So I should have 7. 7 minus 7 times 1 is 0. Minus 2 minus 7 times 0 is minus 2. Minus 13 plus 7 is minus 6. And minus 22, or 22 minus 14 is 8. And then I got a question, is it positive or negative 2? So that would be looking at negative 2 minus 7 times 0. So I think it is indeed negative 2. Okay, so we've got our pivots. It worked. Got the zeros in place. So next up, we're happy to see that there's already a 1 in that next pivot position. And so we got to use that pivot to get rid of the negative 2 that's below it. And so we can take row 4 and add 2 row 3s. And that'll give us our new row 4. All right, so what are we trying to do here? Well, the only thing that's changed is the fourth row here. So we'll still end up with 0, 0, 0, and then a new 0.
Yeah. And 0.
Okay, what form are we in now? Yeah, exactly. This is from echelon form. Is it reduced row echelon form, or is it just echelon form? Yeah, it's not reduced, it's only echelon form. What do we need to take care of in order to get this in reduced row echelon form? Yeah, so the columns from Seche, the columns with pivots need to have other numbers be 0. We have a problem basically here, and we have a problem, and so we got to take care of those two. You can do it in one step, but because we need 2 changes on the same row, we'd have, like, I guess, do you want to do it in one step? Because, so we need row 1 minus row 2 plus 2 row 3 to become our new row 1. And this will do the whole thing for us. Let's see if we can make this work. So the only row that's going to change is our row 1. Okay. So we want row 1 minus row 2 plus 2 row 3 to be our new row 1. Let's see how it all works out. So minus 2 minus 0 plus 0. 1 minus 1 minus 2 0 plus 2 minus 5 plus 1 minus 4 plus 6 is 2. 13 minus 2 is 11. Minus 8 is 3. Okay, and so what I want you to notice here is you have the pivots are all 1s, and everything else in the columns with the pivots is a 0. Yeah, from Ahmed, is there a reason to keep the 0 row in? And from James, yeah, there is. We just need all that information. Let me go back to the beginning and just show one more thing, and that is that this part right here at the beginning was like our forward phase, and this part back here would be like our backward phase. By backward, it'd be like, it's like the substituting, it's like the back substitution. From Ahmed, what's the information that row has? At the very least, that row tells us that we started with potentially 4 equations. So it tells us that one of the equations that we started with was redundant.
Can I have a question?
Go for it, Hui.
So we can just combine any row we want to create a new row, right?
Mhm.
Like in the first step, like we take row 4 and let's do 3 row 2. Like it's not necessary to like take row 3, right?
Right. We could.
No, I just mean like we can just take whatever row we found it necessary to do it.
These steps are not unique. there were other ways of getting the same result. So I think that's what you're asking. Yeah.
Yes.
If you write a computer program, your computer program won't think this way. But for us, we're thinking a little bit. So for example, your computer will probably won't ever come up with that as a first step, because your computer would just divide by 2. I'll just divide by 2, and the computer doesn't care about fractions. But we don't like fractions as people because they make the arithmetic more challenging.
So Dusty, we can solve this in multiple ways, right?
Yep. And if we do it right, every single way should end up with the same result. Like the middle steps would be different, but the end result will be the same for everyone. All right, let's keep going. So we can, I want to talk here about what does this actually mean. So what this means is that first equation, or that first line, is telling us that 1x1 minus 2x2 plus 2x5 is equal to 3. And the second line is telling us that x3 minus x5 equals 2. And the third line is telling us that x4 plus 3x5 equals -4. And so we can write this in a special way. So I'm going to kind of give you a foreshadow of where we're going. So your actual solution, yes, you have 2 free variables. That's correct, Ben. So your actual solution is like x1, x2, x3, x4, x5. Okay. And if you look at it, we can see you've got an equation here at the top for x1. We're saying x1 is like 3 plus 2x2 minus 2x5. And there is x2 is just going to be x2. x3 is going to be 2 plus x5. x4. Sorry. And then x4 is going to be, what do I have there? -4 minus 3x5 and x5. Something like that. Which you could in turn write as you could split it up as 3, 0, 0, 2, -4, 0, plus x2 times 2, 1, 0, 0, 0, plus x5 times -2, 0, 1, -3, 1. In this case, these variables here, the x2 and the x5, get a special name. These are called, like Ben said in the chat, these are called, oh, come back to me. These are called free variables. The others that rely on those variables, on those free variables, are called basic variables. So Tommy's question is, so free variables are variables that repeat more than once. Actually, the free variables are the ones that are in columns without pivots. So notice in that matrix that the free variables were x2 and x5. Those are in the columns without pivots. In example 5, which columns do not have pivots? Which columns down here don't have pivots? Yeah, 3 and 4 from Megumi, from Sam, from Felix. Yep. So those are going to be your free variables. And so to find the general solution of the linear system in example 5, you would write this result sort of like we just did in the last one. This next theorem talks about existence and uniqueness, and we will be talking about that more over the course of the quarter. But it says that a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. We talked about this yesterday. We can't have that 0, 0, 0, 0, 0 B where B is non-zero. If it's consistent, then it'll either have a unique solution or it'll have infinitely many solutions. So let's see what's going on. Is this example in A consistent or inconsistent, and is it a unique solution or infinitely many solutions? So is it consistent? And how do you know? Yeah, it's consistent because you don't have the 0, 0, 0, 1 or B, and because you don't have, there's no free variables. So since there's no free variables, we would know that this is going to have a unique solution. The next one, consistent or inconsistent? Inconsistent because of that last row, good. And then in C, consistent or inconsistent? Consistent, good. And how many solutions?
Infinite number of solutions.
Infinite number of solutions because of the fact that you have those free variables.
Yeah, and then in the bottom row is completely zero.
You could have, it would be okay to have a bottom row of zeros, and you could still have a unique solution. So for example, on this one up above, if we put 0, 0, 0, 0 there, it wouldn't have changed it. We still would have been consistent and unique. So like I remember being confused about that as a student, but it's not the row of zeros that gives you an infinite number of solutions. It's the free variables. So sometimes they go together.
Dusty, so the augmented part, the result part, what if it's 0 and then we have like pivots for the other part? Would it be consistent or inconsistent?
Can you say that again?
For the result part that we added an augmented matrix, what if it's all 0?
If it's all 0, then it will always be consistent. If you have stuff and then you have zeros like this, it will always be consistent. Yeah, that'll be fine. Did that answer your question?
Yes.
Awesome. And then from Seche, we just had an extra equation that we didn't need, basically. Yeah, exactly. What's going on in this example C is that one of the equations was a linear combination of the other equations. Yep. And then to Malcolm, I'm not sure on the notes. I think they should be similar. I think they should be the same, but I'm not 100% positive. The last thing here is the process. So for those of you that have had programming, this is the, what do you call it, like a pseudocode, I think. So this is like the steps that you're going to take to do the so you write the augmented matrix, you use row reduction to get it in echelon form. Once it's in echelon form, then you can tell whether it's consistent or no solution or unique. And then assuming you need to, then you keep going, you do your backward substitution. And then when you're done, you write your solution. We've got stuff about vectors and how to multiply vectors and what it looks like, and the parallelogram rule for adding them, and what it looks like on a grid, and how it would happen in 3D. And the first place that I want to stop is right here, and say that we're going to be dealing with vectors that are oftentimes in Rn. And so when you see this notation, the U1 is telling you that it's the entry in the first row. U2 would be the entry in the second row. Usually it's Bono. And then UN would be the entry in the nth row. So if I had a vector that was like V equals to V1 to Vm, how many dimensions does the space that this vector lives in? This would live in Rm, something like that. So good call, folks. So when we talk about properties of vectors, here we're going to be saying it doesn't matter what order you add them. You can reassociate, you can add a 0, there's an additive inverse, you can multiply by scalars, there's a 1. All of these properties are things you probably get, but the thing that I want to point out again is that this is going to be an Rn. You can't assume that your vectors are going to be like 2-dimensional vectors or 3-dimensional vectors. You'll have to assume that they are in Rn. So what that means is that if we have U and V in Rn given, then this is telling us that U is equal to U1 all the way to UN, and V is equal to V1 to Vn, something like that. So this idea of an n-dimensional vector can be confusing in the beginning, and so I just wanted to make sure that we touched on it before we left class today, so it'll make it easier for us when we pick up again tomorrow.